Thanks, Seb. And thanks everyone for coming, and especially thanks to everybody who proposed talks. It's a really great lineup. I'm really excited to see some of the stuff we're going to talk about today. So I'm going to talk today about span. So span is a new feature that was added in Swift 6.2, and we're finding that it's rapidly becoming a really important foundation for creating really fast code that matches the performance of C while still preserving some of the important safety guarantees that Swift is known for. And to put this in context a little bit, I'm going to recap a sort of a framing that I gave at the Swift on Server conference last November. So when thinking about languages, as I'm sure we all do, because we're all language enthusiasts, that's why we're here, I like to think about how a language performs in three really important categories. How good is it at writing code that's safe, free from memory safety issues and data race issues, things like that? Is it easy to write code in that language? And is the code that you write fast at runtime? And so we can put up some of our favorite languages against these criteria. Favorite is subjective, I guess. In the case of C, the defining characteristic of C is that it is not safe, but it is pretty fast. Obviously, you can always make any code slow, but generally, by default, C code is very fast. But it's not safe, and I would say that that's why it's not easy to write. You have to have a really solid understanding of really complex things like pointers and why they're safe and why they're unsafe.
Sorry. So that people in the back can listen to you.
Microphone's lunging at me. Is that better? Yeah. Okay, cool. Sorry about that. All right, and so yeah, so C is not easy to write because in the main part it's not safe. It's also not easy to write abstractions that make it easier and more productive to write code, and that was what C++ attempted to solve. Does that mean that C++ is easier to write? Well, in some ways, yes, but in a lot of ways, no. In part, again, because it's not a safe language. But it remains a pretty fast language by default, though it's easier to get that wrong the more abstractions you add. And then, of course, Java was wildly successful in the 90s because it was safe by default, but it also allowed you to be really productive. It was really easy to write code that was very expressive. And was it fast? Well, it can be fast. You can write really fast code, and technology around JITs and JVMs have got even better than they were before. But it's a bit of a longer walk. You have to write code that is maybe not as idiomatic as regular Java code in order to get that almost C-level performance. And so these three characteristics are an interesting way of classifying languages, but really we should rule one of these out, right? We should rule safe out as an optional thing. Any language coming out in the modern day should really only be safe by default. And so really we're talking about easy versus fast. And I like to think of this kind of like a slider where you can go from easy code that's easy to be productive in idiomatic code in that language, and you can also at the same time move the slider, maybe write slightly less easy, slightly less idiomatic code, but that is faster at runtime. Now, some languages have this slider further apart, right? You have to sometimes do a lot more work in a language to go from easy and idiomatic to fast at runtime. And I would say Java is probably a little bit like that, right? You can get fast Java, but you have to move the slider a long way to the right in order to get it to be highly performant. Some languages can't be made fast, right? Like maybe you would classify Ruby as something like this, where they only really prioritize sort of expressiveness, and it's a really great expressive language, but you fundamentally hit a certain stopping point. Some languages, maybe one language in particular, is fast by default, but it is pretty hard to write in, even when performance doesn't matter. And that's actually a really important point, which is, in most cases, this level of really highly tuned performance isn't that important for most use cases, only for some. Of course, there are some languages that are neither easy to write nor easy to make performant, and those are the ones we learn for fun. And Swift, I think, what really drew me to Swift is that, in my mind, Swift is an easy-to-write language with highly expressive syntax and idioms, but it's also not very far away from making it performance. The easy-to-write code is pretty good performance by default, and it's not that far to take that code and make it highly performant as C. Except there was a bit of a wrinkle, which is until recently, you did have to use some unsafe techniques to get the absolute maximum performance out of Swift. And my contention is that features in Swift 6.2, in particular span, but also other features like non-copyable types and inline arrays and things like that, finally gave us the ability to retain that highly safe, expressive language, whilst also getting performance down to the level that you could expect from C. So what do we mean when we talk about writing code that's super performant? So here's some assembly. Obviously, all of you know what this does. I'm terrible at reading assembly. My favorite trick these days is to actually cut and paste assembly that I get out of instruments or something like that into an LLM. It's a really good LLM use case where it does a really good job. It even knows usually where the assembly came from, what language, and often gives you tips about what you might change in that language to get slightly better code generation. This is a loop that sums some doubles in an array. And it's actually really amazing to me that you get this really tight code, the same code you would get out of C if you wrote this loop in C, out of this actually, if you think about it, really high-level operation, this reduce operation passing a higher-order function of addition into an array of doubles. And why is that so surprising to me? Well, Swift is a fairly complex language, and the complexity comes from lots of different places. So for example, array here has all sorts of features. It's much more complicated than C's array type, which is really just a pointer. So it's got reference counting, copy on write support, uniqueness checks, exclusivity checks, things like that. And the reduce operation, this is the cut and paste of the reduce operation from the standard library. This is also a really high-level function. It's a higher-order function. It takes another function as an argument. It operates on sequence, not directly on array. And it's generic over any element type. And in fact, array's implementation of sequence is also even more code. And so if you actually spelled out all of the code it takes to do that really simple one-liner of summing an array of doubles, it's actually hundreds of lines of code. And yet the Swift compiler is able to crunch all of that down with the power of LVM and get to the point where it's really this tight code that is just as good as if you've written it by hand in assembly. And that's the happy path. But it's easy to fall off that happy path. And as your code gets a little bit more complex, or you throw in more abstractions and things like that, you get slightly more complicated assembly. So this is an example of the assembly you get if that reduce operation was not specialized. Hopefully you can all read that. I had to make the font a little bit small to fit it in. But this is the assembly you get for if you didn't specialize the reduce operation on array down to an operation on the underlying pointer. And there are lots of reasons for why this can happen. And this code is fine for reasonable level performance, even in this case. But if you really want to match the code you'd get from C, you want to get it to something like this. And the question is, what can you do at a higher level in the Swift programming language when you're writing code that gets you to this kind of level of performance? And a lot of it comes down to using fewer abstractions and helping the compiler get closer to the code that you actually want it to generate. And so one technique that a lot of people use when they want to do that sort of thing is this guy with unsafe buffer pointer. So you've probably seen that, like, experimentally you had some code, it wasn't running as fast as you thought it ought to. You dropped in like with unsafe buffer pointer and it made the code faster. And the reason why it does that is because it strips away a lot of the abstractions and gets really down to a much lower level operation. It gets rid of all of this complexity on array, and instead it says, never mind any of that, just give me an unsafe buffer pointer, which is really just a pointer, an account for how much memory it's pointing to, and it points directly to the elements. Doesn't do any reference counting, doesn't do any ownership checking or anything like that. And that's good for performance, but it's not good for safety. And why is that? Well, if you've ever seen code like this, you should hopefully know not to do this. What this is doing is getting the underlying buffer pointer out of the array, and then it's immediately just returning it. Why is that bad? Well, here's some code in context. Let's say we've got an array. It's a local array. It's declared in a function. You get the pointer out of the array, and then you just return that pointer. And Swift will let you do this, but it would be very bad if you do this, because that array is going to go away at the end of the pointer, the end of the function, but the pointer still exists. So to visualize what that looks like, you create the buffer pointer. The array goes away at the end of the function. Now the pointer is pointing to nowhere land. You use it, and it blows up. And at best case, you get a seg fault. Worst case, you get memory corruption, maybe even an exploit, something like that. So why is span better? Well, span, on the surface of it, looks exactly the same as an unsafe buffer pointer. All it is a pointer and a count. What makes it safe is statically, the Swift compiler will stop you from misusing it like we just saw with unsafe buffer pointer. So you can get a span out. Notice that there's no block constraining when you're supposed to use this. The block has gone away, but you get that span out of the array. You can use it to do things like pass it to functions. But if you try and return it from this function, the compiler will stop you. And the compiler stops you because it knows that span is tied to the lifetime of the array that you got it from. And so statically, it can say, okay, if you're trying to make this span exist for longer than the array would exist, that's not allowed, and it'll stop you doing that. And so span allows you to get a lot of the same characteristics of low-level performance from a pointer, but without the unsafety that comes from a lack of lifetime guarantees. And this really works in practice. Here's an example of some code that went up as a PR against the Swift homomorphic encryption library that's available on the Apple GitHub. Homomorphic encryption is this fancy new encryption technique that allows you to do operations on still encrypted data without decrypting it, which means it's privacy preserving. It means you can do operations for your users without actually having access to their unencrypted data. But it's very computationally expensive, and it was really important to the team that wrote this that they get absolute maximum performance, that they weren't giving up any performance versus C. And when they originally wrote it, they had to use some unsafe buffer pointers because they really needed things like auto-vectorization that would only work when they were operating at a lower level of abstraction. But what we found is that by applying span to this existing code base, we could replace that unsafe code with completely safe code. This is just as safe as doing operations on the array, and you got the same performance without giving up safety. So it's a really valuable technique that we think is useful to apply. So that seems really great. So you might ask, why not use span for everything? We should use span everywhere. If the black box is so safe, why not make the entire plane out of black boxes? And the answer is because you might consider the fact that this doesn't compile is pretty annoying. Sometimes you really do need to return things. And so span today is really useful for local optimizations. So it's available for use now if you want to go in and say, just like you used to with unsafe buffer pointer, okay, how can I make this code faster? But you should still think in terms of objects like arrays, or maybe unique arrays, which are available in the Swift collection package that are non-ref counted arrays that use a different performance feature of non-copyable. And so this is a good example of how you can get more control out of the language by moving away from the simple thing. It's obviously easy to pass around arrays of arrays and things like that. But if you want to put a little bit more effort in, Swift now has these slightly more powerful features that involve knowing a little bit more about the language in keeping with Swift's progressive disclosure that allows you to get better performance by putting in a little bit more of the language's more advanced techniques. So here's one more use case that might be worth thinking about just to motivate you. So suppose you've got a function on your business logic type. So you've got your own user-defined type, you've got an array of those things, and you want to do some operation on array that applies some kind of business logic that you've written. And this works great. The nice thing about this is not generic code. This is all fully concrete, so all of the types are fully understood. But then you hit a problem because sometimes you don't have an array, you have an array slice. And there's a solution that most people know about this, which is, okay, you can make this code generic. It's a pretty easy change. And now this code is generic over any different kind of collection. It'll work on both array and array slice. And this is great. This is a good technique to apply. It does have downsides, though. So what it means when you create an array like that is really what it's going to do is it's going to stamp out two versions of this function. And that's probably fine. But there is another way you can do it that doesn't have this problem, which is you can actually just write this code on array slice. And that way, you don't need to write generic code. You just write the code on array slice. And then when you want to run it on an array, you just turn the array into an array slice. And so that's an alternative to using generics. Which one is better varies depending on your use case. But this use case is useful. But let's say you're using some of the newer features in Swift and you find yourself with an inline array of your objects. this array slice technique no longer works. And in fact, there's not even currently a protocol that unifies inline array and sequence. So you actually can't do either trick in this case. Or maybe you're importing the collections and algorithms packages, and you're using unique array, which is, like I said earlier, another kind of array that lets you operate in the same way as a regular array, but with non-copyable objects. That also doesn't conform to sequence. But all four of these types can supply spans, because they're all held in contiguous memory under the hood, and so they will all give you a span. And so span is also a new way to write code that is polymorphic across lots of different types of containers, and at the same time allows you to write code with pretty much the same idioms that you would under regular code. Finally, here's one example where that doesn't quite work, and this is a little bit about where the language might be going next. So maybe some of you have seen in the Swift collections package, there's a thing called a deck. Sometimes it's called a ring buffer. And a deck does not supply a span method. And there's a good reason for that, which is to do with how decks work. So a deck is short for double-ended queue. And so you can have a deck, it looks pretty much like an array, and when you start using it, it behaves exactly like an array. You put your objects in. I don't know why I chose bunnies here, but it just looked nice in the drop-down when I picked it in Keynote. You can use it just like an array. You can push elements onto it. But you can also pop elements off the front, and what that means is it frees up the space at the front. So this means it's a double-ended queue. You can consume and push and pop from both ends simultaneously. And then you put a few more elements into it, maybe pop a couple more. When you get into this state, when you now push elements into it, what happens is it wraps around. That's why it's called a ring buffer, because it wraps around like a ring. And so now at this point, if you wanted to provide a span into this object, you really need to provide two spans. This is the first span. This is where the first elements live. And you can provide that as one single contiguous block of memory. And then you can provide the second lot of elements as a second span. And this is still fairly simple, but it doesn't fit into that original idiom of like, just get the span out and pass that. What's the solution to this? Well, there is a proposal that we put up on the Swift forums that I recommend you go and look at, and it's about the future of what iteration is going to look like in Swift in this new world of spans and non-copyable types. It's called borrowing sequence, and the idea is that it's a new sequence type, very familiar to the old sequence type, that will allow you to do for-in loops and things like that, but on more types that don't support copyability and escapability. And at the heart of this algorithm is it's got a new iterator type, and that iterator type is based on bulk iteration. So instead of getting one element at a time, what it's going to do is it's going to give you a span at a time. So the iterator, make borrowing iterator that you get out of any of these types, is going to have, instead of a next element property, it's going to have a next span property. That's going to give you a span, and then you can use that span to iterate the elements, and that's going to be much faster. One interesting thing is this ought to make iterating various different collections much faster at debug time, which I think is actually something that's going to come up later. So I think somebody is giving a talk about using span to make debug builds faster, which is another interesting use case. And so this bulk iteration is interesting because if you think about it, what's going to happen with DQ, or DEC, is that you're going to call next span, it's going to give you the first span, and you're going to call next span, it's going to give you the second span. And so that's where the language is evolving and the standard library is evolving to match some of these patterns. And if you haven't already, I suggest checking out that proposal and reading a little bit about it, maybe thinking about how it might affect your code. Of course, that's not the main reason for that proposal. The main reason for this proposal is that really we want to get back the one ergonomic thing that spans still lack, which is you still can't use for loops with them. And this proposal actually introduces the ability to get that feature back, which is much missed, and ought to make spans even more ergonomic and closer to the kind of nice idiomatic code that you're used to writing on arrays and things like that. And it will also give spans the ability to be extended, just like you can sequence with algorithms. So, for example, you will be able to reduce your span of bunnies into their hutch. So yeah, that's a quick tour of what's interesting coming up in the new upcoming changes in the language, and I would urge you to go to the forums, check it out, and give us your thoughts on what it looks like. Thanks a lot.